welcome to the Rancho Mirage Library and Observatory. Thank you so much for being here. We really appreciate you being here. As we get going, I want to give a special thank you to the Rancho Mirage Library and Observatory Foundation. It's through that foundation that we're actually able to have these events and bring in wonderful speakers like Kevin. So thank you so much to the foundation. Now, I will note after our lecture today, there will be a period where you can have some Q&A, but we will also be having an open house out in the observatory, basically a nice tour time, as well as later on, we will be showing Cosmic Dawn, the documentary about the James Webb Space Telescope, and we'll wrap out the evening tonight with, well, hopefully stargazing if the clouds clear, but we will also be doing something inside the observatory dome if the clouds don't. Now, without further ado, more about our speaker. Our speaker today is an astronomy professor and researcher on the James Webb Space Telescope NIRCam science team at the University of Arizona's Stewart Observatory. His research focuses on hunting for ultra-distant galaxies from the dawn of time, supermassive black holes that grow secluded by dust, and cold brown dwarfs at the edge of the Milky Way using the unprecedented power of the James Webb Space Telescope. He received his bachelor's degree in physics from Harvey Mudd College in 2006, and he earned his master's and PhD in astronomy at UCLA in 2008 and 2012, respectively. Not only has he actively worked to advance our knowledge of the universe through his research, he also has a passion for science outreach and education, which has brought him here today for all these fun events we're having. So please join me in welcoming Dr. Kevin Hainline.
Hi, everybody. Thank you for coming out on a Tuesday afternoon to see a pretty fun talk about a very exciting thing that humans have done in the last 5 years. I'm Dr. Kevin Hainline, and I, again, want to thank the Rancho Mirage Library and Observatory for bringing me out here. It's an incredible privilege to be able to talk with you all on a Tuesday afternoon, and thank you for coming in. And please do stay and watch the documentary. I'm going to show some behind-the-scenes photos from my experience working on commissioning and testing the telescope. It's a very, very exciting documentary, and it's a very exciting telescope. So let's get started. As was said, I'm Kevin Hainline. I'm an associate professor at the University of Arizona, and I'm very excited to say that I'm here to tell you about the most exciting thing I've ever been a part of. Now, I should put an asterisk there because also my marriage to my wife is the most exciting thing I've ever been a part of. My wonderful family is the most exciting thing I've ever been a part of. But academically, this is the most exciting thing I've ever been a part of. I have to say that because they are in the room right now. And what that thing is this here. Now, I can't see your hands very well, but actually a little bit now that it's blue. If you've never heard of this telescope, raise your hand. Don't look around, just let it, oh my gosh. I was saying, there are people in this room who've not. I'm very excited. You are so lucky to be able to hear about this amazing telescope today and what it's done. What we're going to do today is I'm going to introduce this telescope. I'm going to show some of it, the background behind the telescope. I'm also going to show you a little bit about what it's done in a broad sense, and then I'm going to focus in on what I use the telescope for as part of a team called JADES. And at the end, I'm going to show you cutting edge, hot off the presses work that I've been doing in the last month or so, including some really exciting research about some of the farthest galaxies. So let me just start by saying, if you've never seen this before, this is NASA's JWST, the James Webb Space Telescope. It is probably the most complicated science project NASA has ever undertaken. It is a 30 years in the making telescope. It is worthy of many documentaries because of how much work went into and planning and execution on putting this thing into space. But first off, you're looking at this and you might think this does not look like a telescope. Because you imagine what a telescope looks like is the emoji, a tube. You look through one end of the tube and see space. Telescopes are designed to take a lot of light and kind of funnel them down to a smaller region. And this does exactly what the telescopes you're familiar with, or the telescope that Galileo first used in the 1600s, it does the same thing, but it's a lot larger. And so instead of using a lens like the tube telescope you might have gotten at Sharper Image, this uses a giant mirror. So this is a telescope with a mirror that focuses instead of a lens. This is the mirror here, the primary mirror. We'll get into that in a second. Now, Mirrors are used by most large telescopes because lenses have some problems with them in terms of their weight and in terms of the fact that they don't bend light at different colors the same way. So mirrors are commonly used, but as you all know, because presumably you've looked in a mirror takes the light and bounces it backwards. And that's not particularly great because you want to capture that light. And so in order to capture the focused light, there's actually a second mirror that's hiding right behind these little arms right here, the secondary mirror. So a telescope like this takes light from space off on the right, and it focuses it onto the secondary mirror and into this little box back here, where on the back side of the mirror are a series of cameras. The cameras are what I'll be talking about in a little bit. And then it's also sitting on this big silver thing, which is not typically part of telescopes, and we call it the sun shield. I'm going to talk about every aspect of this, but I assure you, this is a telescope. And it's the successor to NASA's very successful and very tube-like Hubble Space Telescope. So let's talk about that primary mirror here. This is almost, the screen is pretty big, almost to scale, showing you myself down here. Each one of these boxes is a meter, a little over 3 feet. And you can see this blue circle represents the mirror for the Hubble Space Telescope. Hubble was put on a space shuttle in 1990 and put in orbit around our planet. It has essentially changed astronomy in its many years in space, taking pictures of the entire night sky, very, very famous pictures you've all seen. And it did so with a mirror that was a little bit taller than me, and a little bit taller even than Shaquille O'Neal here, this famous basketball player. This is the size to scale of NASA's JWST mirror. And it's composed of 18 hexagonal mirror segments that, if you can see here, are about this big around. Each one of them is covered with a little bit of gold, a very thin layer of gold, because gold reflects the type of light that this telescope sees particularly well. If you were to take all the gold off of this, you might think, wow, it's a nice sense. Someone might steal that telescope and get the amount of gold is about the size of a golf ball. That's the amount of gold. Smear that out over these 18 hexagonal mirror segments that are spread out across 6.5 meters. So I'm going to cough. And as maybe you aren't familiar with how big that is, well, that's essentially about, I don't know why this is not clicking. Oh, yeah, oops. This is a little bit slower than I want it to be sometimes to click. So let's click forward. Okay, excuse me. And there, and here, there. It's about 3 Shaquille O'Neals, or 4 fridges, you might be familiar with fridges, or 1 adult giraffe, or for the Star Wars fans, it's about 6 R2-D2s in height. It's pretty big. It's a pretty big mirror, right? Again, it looks pretty large here, and look at how tiny I am compared to it. It would kind of barely fit inside of this room on the ground. The whole telescope itself would not fit inside of this room. It would be too tall to fit in this room. The Hubble Space Telescope, by comparison, is the size of a school bus. You could park a school bus in here pretty carefully. Be careful, you have to move some of the walls out of the way. But by comparison, it's a much larger telescope. And the cameras that the light goes to, there are 4 of them. And the one that I'm most interested in, and I'm going to show you a lot of pictures from this camera, is a camera called NIRCam. This is NIRCam right here. It is a very, very important telescope instrument. It is the workhorse of the telescope. Many of the very famous images you might have seen from the telescope were taken by NIRCam. The PI of NIRCam is a woman named Marcia Ricci. Her office is 1 door down from mine, so I see her all the time. And she worked, probably 20 years ago to essentially design this telescope instrument. And it's actually 2 cameras that are identical. And you can see that all of the things up on the top are on the bottom. Now, you might be familiar with a camera that a digital camera or your cell phone camera. This operates a little bit differently. It has some wheels, these big barrels that you can see up on the top. Those are filters, and the actual cameras themselves, the detectors, are in these boxes right here. Light comes from the telescope, bounces off of these mirrors, and goes inside of this, but that means it takes big rectangular images. It has 2 squares, because 2 cameras that are identical, taking 2 images that are squares, making 1 big rectangular image. And that's great, because area on the sky is pretty important. When you have limited amount of time, to be able to take big, wide images instead of 1 smaller image is pretty helpful. NIRCam, the NI in NIRCam, I'll talk about in a little bit, but the other instrument I want to talk about a little bit also is another University of Arizona instrument, which is called MIRI. And MIRI is a mid-infrared instrument, so it's actually advanced. MIRI is a mid-infrared instrument, which is why it says MI. Again, we'll talk about that. But MIRI is a detector, our camera that was on the chopping block. This telescope was around for in process of being built for many, many years, and they thought, this is way over budget. We're going to have to take stuff out, and this was one they were going to take out. And I'm bringing this up and telling you that to show you that sometimes you have to fight. You have to fight to keep things on and keep functionality because this is a very exciting instrument, and some of the things I'll talk about at the very end were only enabled by the fact that this instrument was successful and was put on the telescope. So let's talk about light for a second. Let's back up before I get too in the weeds about how these cameras work. I'm talking about near infrared, mid infrared. What does that mean? Well, let's talk about light. So this is the electromagnetic spectrum, meaning all the possible flavors of light. Up on the top, I'm showing them from gamma rays, which are the type of highly energetic light rays that turn you into the Hulk, to X-rays, which is what you put a lead shield over your chest at the dentist's office so they can see how your teeth are, or if you get an X-ray of your bones, you use X-rays. Ultraviolet, which is why you wear sunscreen here in the desert, because the sun gives off ultraviolet light, and you want to wear some cream that reflects that back to space. Then you have this tiny little window that we barely care about called all of the light that you see, visible light. And then you have infrared, which is my favorite type of light, which is a little bit longer wavelengths, and it's the light that we'll be talking about throughout this entire talk. And you can keep going to radio waves, which is the type of light that your cell phone emits. Your cell phone is a very fancy flashlight that emits radio waves that go talk to other towers that just essentially collect radio waves. And when you listen to the radio, you're listening to light that has been turned into audio through your computer's speakers, But all of this is just light. It's all wavelengths of light. And visible, the stuff you're familiar with, is just where the sun is brightest, which is why your eyes are sensitive to this. If the sun were much fainter or much more brighter, our eyes would have different sensitivity. But there are animals and bugs that are sensitive to ultraviolet and infrared light as well. And in fact, if I had an infrared camera right now, you would all be glowing in the infrared because you're warm and your skin gives off infrared light off into space. But over here at the shortest wavelengths, it's blue. Longer wavelengths is red. Lower energy is down here, and higher energy is over here at the shorter wavelengths. But the infrared is very important for many reasons. One, the universe is filled with dust. And dust is pretty important in terms of the fact that you and I and our molecules probably got together initially on grains of dust. And we are made of star dust. But dust is annoying to astronomers because it blocks the light we care to see. And so in the same way that if you look out, well, not here because the mountains are in the way, but if you look out over the ocean, the Pacific Ocean as the sun sets and it looks redder and redder, that's because the sunlight is going through more atmosphere and more dust. And the astronomical world also looks, as you look through dust, it looks redder, it's harder to see. Hubble was limited. It couldn't see through that dust. But infrared light passes right by dust, does not care about the dust. So if you have an infrared camera, you can see through the dust. And you might know this because, firefighters sometimes use infrared goggles when they're going through smoky houses to find things like your cat or a person because they can see the glowing light of that cat or person through the dust. And astronomers do the same thing with telescopes. But for what I do, and we'll talk about this more later, the universe, as you go farther and farther away, the light is stretched to longer and longer wavelengths through something called cosmological redshift. And that means all the exciting stuff is pushed to longer and longer wavelengths in the infrared, farther than what Hubble could ever see. Here are the four instruments and what wavelengths they cover in the near and mid-infrared. Near is over close to optical. You can see the little rainbow they have here of optical showing that. NIRCam, NIRSpec, and NIRISS are three of the primary instruments that operate at around the same wavelengths. And then MIRI is the one that operates at longer wavelengths. Marcia Ricci, the PI of NIRCam, she's the most important person for getting NIRCam on the telescope and working the way that it does. She is a real NIRCam booster as a result. But I asked her, before the telescope launch, which instrument's probably the one that you're the most excited about? And without missing a beat, she said, MIRI. And she's right. MIRI is the one that operates unlike all the other ones. It's a really fascinating instrument, but it's kind of like going to the manager of like a baseball team and being like, all right, so you manage the Dodgers. Who's your favorite team? And him just without missing a beat, the Giants. No, whoa. It's the wrong instrument, right? But no, NIRCam is the one where she knew it would work. She knew exactly what it would do. MIRI was the one where she thought, we don't know what we're going to see when we look in the universe with MIRI. And again, I'm bringing that up just to set myself up later for some very exciting discoveries we've made with MIRI. So, the telescope was built over the course of many, many years, and that is the whole subject of the documentary that's going to be shown later. If you want to come see all of the stuff that went into going and making the telescope and putting it together, all of that is shown in the documentary. But I'm going to rush ahead because we want to get to the exciting science to maybe the most nerve-wracking day of my life, which was Christmas of 2021. because that was when they put my entire career on the top of a rocket, and I had to watch to see if my career exploded on YouTube live. In French Guiana, they'd put this telescope on a boat down through the Panama Canal. The Atlantic magazine had an article that literally said, "Will pirates steal the James Webb Space Telescope?" I don't think any of you have ever had to worry like I did about pirates. And then they stuck it on a rocket, and I sat up. I couldn't fall asleep that night. I have a picture that I will not show for her sake of my mom bleary-eyed waking up at 4 a.m. to keep me company as we waited the next hour or so before the launch of this. And the thing was put on this rocket, and the Arianespace, a French company, launched it into space. And the rocket launch was incredibly successful. And I'm going to show one of my favorite videos here. It's going to be a little loud because it's got some audio, but this is a video of it after it's launched, and they've pushed it off of the rocket. The rocket's tumbled back to Earth, and they're pushing the telescope off towards its final journey here. You can see it from a camera on the rocket, watching as James Webb flies off into space here. Just push it off, and you're looking at
Webb Space Telescope. Go Webb!
All of these very French folks saying, "Go Webb!"
We do have confirmation of observatory separation. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery.
If any of this had broken, end of mission.
And there is the view from the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
It's like a
fantastic pictures of this telescope.
Go Webb, go Webb!
Yes, go Webb.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
Yes, you're right, Rob.
You can see this thing extending off.
Fantastic pictures. Yeah.
Is a solar panel. If
There
that
is
didn't
the solar
extend,
array having been deployed.
It would have
James
broken.
Webb now has its array out as we stand by for confirmation that it is power positive.
I was watching this and crying and crying.
Hey Rob.
Because this was at the time a culmination of many years of my life and many people's lives, and it was one of the most beautiful things I'd ever seen
Call. James
academically.
Webb not only has legs, but it has power as it begins its journey and the commissioning activities to follow.
So let's talk about that line in just a second, the commissioning activities to follow. You heard the person say it had to go 1 million miles away. This is a diagram showing to scale the Earth, the Moon, and then 4 times farther where JWST lives. It is not traveling out to the things it's taking pictures of. It's parked in an orbit in a system around the sun, but it's parked in a spot called L2, or the Lagrange point 2. And it's parked there so that it can take that beautiful sun shield I told you about, the big silver sun shield, and just point it so that it keeps the telescope in the dark. The Earth and the sun combined put off a lot of light, and that heats a telescope up. And you don't want to take pictures in the infrared if the camera that you're taking pictures is glowing in the infrared. It'd be like trying to take pictures when your camera's on fire. You're only going to get pictures of the fire. And so in this case, you can see down here, the hot side of the telescope, the one pointing towards the sun, is 185 degrees Fahrenheit. We call that Coachella Valley. And the cold side over here is negative 388 degrees Fahrenheit. And that is what you all were watching as the East Coast was suffering from just a couple weeks ago. Happy over here. But it needs to be this cold in order for it to operate the way that it does, which means it had to essentially have all of these parts in the sun shield work. But you're probably noticing and wondering why I skipped past it. Why did the telescope look so weird from the video I just showed you? It didn't look like the telescope I just showed you. Well, remember, it had to fit in a rocket. And to fit it in a rocket, they folded it up. They folded a $10 billion space telescope up like origami to go inside of a rocket. This is how it was folded up. Same telescope. I'm going to show a pretty quick video of the telescope unfolding. It was doing this over the course of a month as it traveled from the launch site at French Guiana all the way out to its parking spot at Lagrange point 2, 1 million miles away. And so the first thing you're going to see is what, you were looking at a shot looking up from the bottom here, this bottom part right here, you're going to see the sun shield, the solar array open up down here first. And then you'll see a little tiny arm open over here that is the radio antenna that can talk back to the Earth, right? So here we are as we slowly start. It opens up, the solar array, then this right here are the sun shield boom arms that are holding the sun shield. The mirror cranes up. The sun shield covers open. These two arms are going to telescope out and pull the sun shield out. 5 layers, each thinner than a human hair. They have to tension out. If any of this broke, any step of this broke, mission over. Every part of this has things where there were what's called single point failures, meaning if one of the little ratchets that held the sun shield cover didn't work, end of mission. I will tell you, I don't think I've ever been more terrified than when this was all happening, knowing that any day I could just get a phone call saying, actually, this part just broke, and end of mission, sorry, because we couldn't get out there and kick it. This was on its way 1 million miles away, well beyond the orbit of the moon, right? We got this thing tensioned, and at this point, the secondary mirror is going to come down on these long arms right here, and then the primary mirror has to ratchet into place, and the telescope was done. And when this happened after a month, it was an incredible, incredible achievement for humans because it all worked. It's why the telescope was delayed so long. It's why it was kind of scary that when we got it to French Guiana, they did the last set of testing and something hit a part of it, like in the testing, and everyone was like, because it's a very sensitive telescope that we did not want to break in any capacity. You'll have to ask me or come to the documentary and hear more about some of the other things that happened during this. But I knew at this point we weren't even close to being out of the woods because this is part 1. We hadn't turned the thing on yet. And at this point, we needed to turn the camera on, and I had to start traveling out to Baltimore Mission Operations Center as we turn the camera on to get it working. And the thing is I'm going to use this as an opportunity. If that part is exciting to you, the idea of what it first looked like, and if you want to see what the actual first light image, not very easy to find. In fact, I don't think you can publicly find it very easy at all. The actual first light image from the telescope, you should come to the documentary. I'm going to show that as part of it at the very end. But I want to skip ahead because I want to get to some of the science to tell you that we got the telescope turned on, all the cameras worked, it focused. In fact, it works significantly better than the nominal design limits that was like, it has to work this well. It's way better than that. The resolution, the sensitivity. It's a telescope that can get us pictures easily like this. This is Pismis 24. This is a local star-forming region, just a number of thousands of light years away, where what you're seeing up and blowing away gas, pushing away gas, when you get these fingers here, which are denser pockets of gas, where all of that light is just pushing the gas away around it, such that you're able to see baby star formation in these little fingers. These are the dense pockets of baby star formation. This is like me taking a picture of a hospital's maternity ward. Except if the maternity ward, the babies were crying so loud all the nurses left. Because that's what is going on. These are crying so loud with light, they're pushing all of the gas away, allowing us to see these beautiful tendrils of gas, right? If I were to look at another one of these star-forming regions, maybe one in a little bit farther away where we can see it all, because this is, imagine kind of looking at the edge of one of them. Here's one of my favorite images the telescope's taken. I love this picture right here. This is NGC 602, and it is a star-forming region in a nearby galaxy that you can see in the southern hemisphere, a large Magellanic Cloud. And imagine, I wasn't because it was a different star-forming region, but the last picture was kind of like a zoom in down on like one of these edges down here, right? You are seeing baby stars as they're slowly pushing away gas. And this matters, seeing all these baby stars, because stars are the sites of atoms being put together. Those atoms are put together and then go into forming new stars and new planets. And as we look at baby stars and planets, we get an understanding of our own shared origins. And being able to see this through the dust is really, really profound. If you want to look, JWST and NIRCam has also looked at the other end of the life cycle. This is a picture from just a couple months ago. This is the Red Spider Nebula, and this is what's called a planetary nebula. It's what happens when a star like our sun dies. Its outer layers puff off into space, leaving the naked core, which is right in the very, very center here. And all of this is hitting all of this gas that already exists. The outer layers are puffing out, and this has all of this gas contains carbon. Carbon is the stuff that is in your skin right now. It's what you're made out of. And you, at some point, all of the atoms that compose you were in a gas cloud like this. You just forgot about it. You don't remember what it was like. probably pretty fun. You were this a lot longer than you were a person, which is an exciting aspect as well. But we can take pictures of this to understand that process in detail we've never been able to see. We can also look in closely at more close versions of that. Here's another nebula. This is the Helix Nebula, and we're seeing, this is the Helix Nebula, just zoomed in on one of the edges. And like all of this is little pockets of gas left over from a star's death. And you see galaxies behind it and stuff. It's just the detail that we have with this camera. And whenever I compare a Hubble version to a JWST version, you can see that Hubble had some beautiful images, but there's always kind of a sheen. You don't see nearly as many stars and things because that dust was blocking the way. NIRCam is a very sensitive instrument. It can take pictures, I'm going to show you later, of some of the farthest things that humans have ever been able to see. But it is such a powerful telescope instrument that it can take pictures of things you can see tonight with your naked eye. Well, if it wasn't cloudy. If it wasn't cloudy, you could go out tonight and look up and see this right here, which NIRCam can take a picture of, Jupiter. I think it's an amazing achievement that the same camera that can take a picture of the farthest, faintest thing can also take a picture of this, because this should blow out the camera. It's so sensitive. But we can do very clever things in how we take pictures so that we can look at a planet like Jupiter in a way we've never been able to see it with this infrared vision, where we can see through some of the upper atmosphere clouds deeper into the planet. That's what you're seeing. These blue right here, the darker regions, are deeper into the planet Jupiter. So we're seeing clouds deeper in and how the chemistry within Jupiter is occurring. And then on top of that, can you see up at the top and the bottom, there's this red? You know what that is? That's the aurora. The aurora jupitalis, or aurora borealis and australis down here, because it just means northern and southern. And we can see that Jupiter has a magnetic field like the Earth, and it has aurora very similar to the Earth. But you wouldn't be able to stand on this big gas giant to observe it, so we can observe it a little bit better from Earth. Just to give you an idea about how big Jupiter is, the great red spot here is like 2 Earths in size, right? It's 10 Earths across. Really a beautifully big planet. Here is another image of star death. This is the JWST image of the Crab Nebula. And I like showing this because this is a star that exploded in 1054. And we know it exploded in 1054 because we have the records of the people who saw it. In China, in the Middle East, and indigenous people in America all saw this star exploding in 1054. If you go up to northern Arizona, there are cave wall paintings of this star exploding. And if you go to ancient Chinese records and look through their record books, you can see that they wrote down new star, weird new star in the sky. And they say exactly where it is, and we look there now and see this star that's exploded. If you take and look at how fast the gas is moving and then trace it backwards, you'll see that it traces all the way backwards to exactly when it exploded. Cultures that never talk to each other, communicating because of their curiosity about astronomy, which is really beautiful. And then one of the other recent images that I think is really wild, this is called APEP, and it's 2 Wolf-Rayet stars, 2 stars that are kind of swirling around each other. And as they do, there's a period where they kick out a lot of carbon gas, which is what you're seeing in these beautiful spirals. This is what happens when you get these 2 stars churning up as they spiral around each other. This, when you watch the ice dancers this week at the Olympics, think about the kind of sprays of ice off of their skates. This is the space version of that, right? Which is very beautiful. So all I've shown you in these images are really an incredible achievement of humanity, but they are a lot of things that is in our neighborhood. It's like I'm just showing you pictures and telling you all about all the cool things you can do here at the Rancho Mirage Library and Observatory. And I showed you pictures of the observatory and the books and all these things, the cafe. Very exciting. But you might be wondering, what's beyond? What can we see that's farther than that? And that's what the remainder of this talk is going to be about. It's what I do for my career. And it starts with an idea that I think is really important, that you have to understand, or else the rest of this will be very difficult to get, which is that with JWST, when we look farther and farther and farther away, we are looking back in time. So let me explain that in a way where in the past, my mother is a really big fan of period piece literature and films. And as a child, I'd sit and watch these movies with her. And most period piece movies are just a series of women sitting on hills reading letters. They read these letters, and then they go, oh, my friend must be doing this, and they have some drama in a tea room somewhere, and then they write more letters. And those letters are something where they write a letter, and if you get a letter from your friend who's in another country, maybe it's a person who lives across the ocean, they would write a letter, put that letter on a ship, and it'd come all the way over, and then they'd read the letter. And no one read the letter thinking, this is what my friend Beatrice is doing right now. They'd think, this is what Beatrice was doing a month ago, or a couple months ago when they wrote the letter. And so time was something where it took time, so it was something where you had to remember, it took time to get the message. Light does the same thing. We just don't ever think about it. Right now you're seeing me, and the light takes like a split second, so it doesn't matter. But for the sun, the light takes 8 minutes to get to us. Meaning when we see the sun in the day, the sunlight, that's 8 minutes old already, flying across the solar system to get to us. If the sun were to explode, it would take 8 minutes for us to know about it. The sun would explode, and we'd have this blissful 8 minutes of like, oh, wow, everything's going great. And then the sun we'd find out the information. And that gets more and more severe as you go farther and farther away. Light hours, light days, light weeks, light months. It takes time to get the information from a distant object to us, such that when we get that information, it's like the letters from Beatrice, we learn about what that object was when the light left the object, not right now. So for distant galaxies, I'm seeing them after their light has traveled millions or billions of years. So when I see them, I'm seeing them as they were when the light left. I'm seeing them in the past. And this means that I can use a telescope like JWST as a time machine to see back in time. The farthest galaxies that I'm looking at I don't even know what they will ever look like right now. I have no idea if they still exist, but I'm looking at them as they were when the light left, when the universe was much, much younger. So here is a pair of images that really changed my life in the 1990s and the early 2000s, the Hubble Deep Field and the Hubble Ultra Deep Field. And there's a huge, documentaries have been made about these two images, but these images were when Hubble aimed at two different patches of the sky, opened its shutter, and said, what do we see when we look out into the universe? And there was some controversy about whether they would see any distant galaxies at all, but luckily, when they took this big picture here in the early 90s, they saw galaxies. Every object here is another galaxy. And a galaxy is like, we live in a galaxy called the Milky Way. It's 100 billion stars. So this thing right here, another Milky Way, 100 billion stars, 100 billion stars, 100 billion stars. Every dot here, except the ones with the spikes, is a galaxy. Some probably have less than 100 billion stars, some have a little bit more, but it's generally, we observe, and in both patches of the sky, it's just chock full of galaxies. If every person in this room looked at a different galaxy, there'd still be thousands of galaxies you had not looked at. No one in this room was looking at that one right there, sorry. I do this every single time, and I've never had someone go, I was looking at that one. Like, I guess if I'd said like this one or something, but this was something that when they came out, I just was captivated. What were we learning about these galaxies? What could we tell about these galaxies? And then as I looked at them and thought about them more, eventually I was like, this is great, but are there galaxies just off the edges of this, if you even went farther? And what happens if we go deeper? Because I could see the inherent limitations to what Hubble could do with observing this. And so, but first, what I want you to understand when you look at an image like this is that every one of these objects has a different distance. They're not all in one big plane. You're looking at them as they far away. So let me just show you a kind of graphical representation of that. If I were to take an image of galaxies and then show you, put little dots, and then show you this kind of like from a side perspective of the sort of thing, where every one of these you give it a distance. And what that means is that as we show this sideways, you're seeing that some are close by, but as you look out to the very edges, you're looking in a big cone, farther back billions and billions of years ago, right? That's what these images represent. If you were a historian, this would be such a cool tool. Imagine if you're someone who's like, I would love to understand the indigenous people who lived on this land. And I could say, well, I could just take a picture of them. And then I take a picture of this crowd right here, and in the background of the crowd are people from the 1920s, and behind them are the people from the 1800s, and behind them are the 1700s. I look way in the back, and I go, oh yeah, there's the first people who lived in this land, way in the back. I can do that with what I look at with astronomy, with galaxies. Just hiding behind the ones that are in the way are farther and farther galaxies, farther back in time. And so the question I asked earlier, which is who's going to go farther? Who's going to look on the edge of those images and look, even farther back in time? That person, turns out, was me. This is JADES, the JWST Advanced Deep Extragalactic Survey. It's one of many incredible surveys that JWST has done of the distant universe. There's ones that are a little bit larger in area but shallower. There's ones that are looking at different wavelengths. There's ones that are really, really, really deep but are very, very small. JADES is, I consider, one of the most comprehensive surveys. It is an enormous amount, probably over 800 hours of time on the telescope to observe these galaxies, and I'm only showing you a tiny chunk of this because I'm kind of trying to zoom in on this. If I zoom out, this is what was public, but currently, as of like 3 or 4 weeks ago, you can go and look at all of these data, completely public. You can actually, at the end of I'll show you how you can do this, you can open this image up in your phone browser and, like Google Maps, zoom around to every part of this and zoom in on the galaxies, click a little button and see what's going on in that galaxy. And you'll see the work that I've done to essentially characterize the distances of the galaxies. And I want to show you this field is very well studied. In fact, it's the site of the rightmost Hubble Ultra Deep Field that I just showed you, which is this tiny little chunk right here. So when I was wondering what's on the other side, I now know. I am the world expert, and unfortunately, knowing every one of these, because I've looked at so many of these little smudgy galaxies in my work, this is a culmination not just of JADES data from our team, but also a lot of other teams that have observed this, different regions, and added stuff to this. And it's not only the JADES region. We have a whole different region, the goods north over here, and the other side, the Hubble Deep Field, is just this little tiny chunk right here. All right, so if you are a person like I was who's wondering what was in that little chunk right there, well, we now know. It's more galaxies. You can notice also there's not that many stars in this, and that's on purpose. We chose these regions, these were chosen years ago, because they were really devoid of stars, because stars get in the way. All of the beautiful images that I just showed you earlier of the nebulae and the gas clouds and stuff, those are just getting in the way of the stuff I care about, the galaxies. And so you would never want to look at a nebula to look at galaxies. Everything's too in the way. You want to look at regions devoid of a lot of stars. And so the main thing when we try to understand this is, well, what's the properties of these galaxies? And one of the fundamental properties is how far away they are. How far away are all the galaxies? Which one's the farthest is maybe the question you might ask. And how do I find the farthest? Well, to start, we have to go back 100 years, a little over 100 years, when Edwin Hubble, using work that was done by a woman named Henrietta Swan Leavitt and work that was done by a guy named Vesto Slipher and work that he was doing at the Mount Wilson Observatory outside of Pasadena, he essentially realized that these people were giving him information, and that when he looked at galaxies, he could say, oh, every galaxy that I look at is flying away from us. Vesto Slipher had discovered this in northern Arizona. Every galaxy that he was looking at is flying away from us. And then Hubble said, and the ones that are farther away from us, probably they're going faster. This is weird. And he discovered an idea called redshift, which is that the universe is actually expanding and the galaxies that are far away are actually moving faster and faster. So let me show you a graphical representation of that. Here's the universe. I've now put little boxes and lines on the universe, and I'm not going to zoom in. I'm just going to park myself. We're all going to sit parked here as we let the universe expand around us, okay? So what you're seeing here is not you flying through space. We're just floating. The universe is expanding. The galaxies themselves are not. They're just flying towards us, and they're all flying away from each other. If you put yourself in any one of these, it would kind of feel like everything's flying away from you because you're not noticing you're also flying through the universe. There's no privileged position. This idea that the universe is expanding and the farther something is, the faster it's moving away from us, means that we can essentially figure out how far away galaxies are by figuring out how fast they're flying away from us. And so what we do as astronomers is we look at our images and we figure out their distances based on the fact that the universe is expanding. If the universe weren't expanding, my job would be almost impossible. Because some galaxies look like they're far away because they're dusty, or they look like they're far away because they're maybe a little bit smaller. Galaxies are not all the same, just like people aren't, right? People are very diverse in all different shapes and sizes, and you can't just make a split judgment based on seeing someone. I can't just look at a galaxy and go, oh, you're far away, because I have, and there are ways you can get tricked. Instead, I got to look for the ones that are moving away from us the fastest. And to do that, I generally want to use a spectrum, meaning I want to take its light and pass it through a prism, look at it as a function of wavelength, and look for some sort of signature that I know should be at a very specific wavelength, but because it's flying away from us, it's been redshifted, pushed to longer wavelengths. This is something that you have interacted with sound all the time. If you go out on the highway here and stand there, a car will drive by, or better yet, a motorcycle, because they're more annoying, and it'll sound like this. And I'm going to do my impression here, so this is the theater of the mind part. It'll go, and that noise shift between high-pitched to lower-pitched, that's because when the motorcycle is coming towards you, its wavelengths of its sound are pushed shorter, it's squished, and so it appears higher pitched. And when it moves away from you, it's lower pitched. Sirens do that. Woo, 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 woo. This is just the Doppler shift of sound, and it happens with light. For a galaxy that's coming towards us, its light is pushed to shorter wavelengths, and the light looks like it's more blue than it should be. And with galaxies that are flying away from us, if they're flying away faster and faster, their light is shifted to longer wavelengths. And if I look at the difference between where they should be at rest and where I see them, I can use that to calculate this number we call redshift. The bigger the redshift, the farther it is. This is maybe the most complicated. If you want to turn your brain off for just a second because you get overly overwhelmed, I understand. This is maybe the most complicated figure right here, just for the dorks in the audience. This is a plot that shows redshift on the bottom. Zero redshift is you and I. We're zero redshift with respect to each other. And as you go farther and farther back in time, you go to far higher and higher redshifts. This is the look back time. You go from 0, look back time, so now, that's what I'm seeing you right now, to 5 billion years in the past is a redshift of like 0.9. 10 billion years in the past is a redshift of 2. This redshift 6 here is like 12.5 billion years in the past. But also, in yellow is how far away it is, right? So for an object of redshift 6, you're seeing it as it was 12.5 billion years ago, but also it's 27 billion light years away. This doesn't really help me very much because the universe is expanding. This is really what I care about, because I care about how far away in the past it is, how far away we're seeing it. And so I'm going to show you an actual galaxy from JADES. This is an actual object right here. It's got the beautiful name of 1028761. Helps me when I look for it in my survey. It's not a very fancy. You can name it whatever you want. Doug. And Doug here, to figure out how far away it is, we take a different instrument called NIRCam and pass its light through a prism. And when you pass the light from Doug here through a prism, you end up getting this little smudge. And this smudge right here, first off, I see it over here, and then this is wavelength. So this is 1 micron to 5 microns in the near infrared. Pass it through. Your eyes are not sensitive to any of this light. You would not be able to see Doug at all, because Doug's light doesn't appear over here, shortward of 1 micron, and our eyes only become sensitive over here. Doug is outside of what you could see with your eyes at all. You need an infrared telescope like JWST and the camera NIRSpec here and NIRCam to actually see it. And do you see these weird spikes right here? Well, let's take this representation and make it into a graph where the spikes are higher, right? So right down here, you see these high spikes, right? I can tell this right here is a spike that comes from oxygen gas. And I know that oxygen gas, if we were to observe it here on the Earth, would be at 0.5 microns. Its wavelength, the light would be over here, but instead it's been pushed all the way out to like 4 microns. I use that little delta, that equation I just showed you, to show the redshift of this object, the distance and redshift of this object, and that is what we can do, by 5.1 or whatever. What we can do with this, it's really, really an impressive thing that we can find distances, 6.76, that we can find distances in this way. I also want to showcase that overall there's like these spikes which come from gas that's like fluorescing, but also there's this underlying line that goes up and then falls down where it says Ly and then it has an alpha. And that little cliff right there comes from the fact that this object has a lot of baby stars, and those baby stars are making a lot of ultraviolet light. They're very energetic. But there's a filter around galaxies, and that filter is hydrogen. And hydrogen absorbs all of the light shortward of this. That's why it falls off a cliff here. It's like if you go to that hospital, all these crying babies, and you put on noise-canceling headphones that just tune out all baby sounds. That right there, that cliff is the Lyman break. This is a more technical thing, but for the people in the audience who want to do a lot of Googling afterwards, this is what you should Google, Lyman break. And I say this because Lyman break galaxies, this technique I'm about to show you, was really, really pioneered by an astronomer named Charles Steidel at Caltech. And Charles Steidel had a suite of graduate students, including a woman named Alice Shapley. And one of her first graduate students was a person named Kevin Hainline. And so this technique that I'm showing you, I'm like the scion of the grandson, essentially this is a technique that was pioneered in the 1990s with the Hubble Space Telescope and with telescopes in Hawaii where they could do this, but now we're able to do this even farther redshifts. And so let me show you something, which is that I can't take a spectrum of every object I care about. I can't do that because that spectrum that I just showed you with the prism takes a long time. I'd love to be able to do this project, look for these distances, find the galaxy distances from images alone. And to do that, I essentially use this technique for finding Lyman-Break galaxies pioneered by Chuck Steidel, where I'm looking for that cliff. And I'm looking for that cliff by taking images at different wavelengths. These are all these little curved lines or just a different filter. And notice that as it goes to higher redshift, this number goes up, the galaxy stops appearing in these filters. It drops out. So these objects are called Lyman dropouts, dropout galaxies. And so what I'm looking for is a set of galaxies where they don't appear in short wavelengths and then I suddenly see them. Here are actual images that I discovered from JADES showing you. I see it in all of these images. Every one of these is a different filter, a different way of looking at this galaxy where I'm throwing out all the light except at very specific wavelengths. And I don't see the galaxy there. And then suddenly I see it in every one of these. I don't see it in here or here, and I suddenly see it. So we call this an F090 dropout because it drops out of this filter. And as this goes out to longer and longer wavelengths, I start to see it only the longest ones, and I don't, and I get the farthest galaxies. And if you do this for 500,000 galaxies and essentially sort, you can find which ones are the farthest. And when our data first came down, we're able, by the virtue of how things slipped on the schedule, we had like a week with which we got our first data, and we could say, if we can get some high redshift candidates, some objects, because these galaxies, there's ways the universe can trick us. These are just candidates. If we can get some really good quality candidates, there's a way we could potentially find the confirm your redshifts, Kevin. These are called photometric redshifts, which is kind of like the hand-wavy redshifts. And so I, over the course of a week, scrambled to look at 100,000 galaxies. And I found 4 objects in our survey, our early survey. We'd had the data for a week that were like, these are the best candidates. Here they are, these objects. There were 3 of them up here, down here. This is where the Hubble Ultra Deep Field was. And when we were lucky, about like a month later, the data got taken by the telescope, all these were passed through a prism, and every single one of them was at the redshift that I had predicted them to be at, including this one, which at the time of discovery was the world record farthest galaxy humans had ever seen, breaking what Hubble had seen by a lot. Hubble's record was about 10.6, and now we're at 13.2. And it's got the beautiful name JADES GSE13, which is helpful for me. JADES is the survey. GS is good south where we found it, like the neighborhood. And then Z13 is its redshift. And 0 is us being cocky that, this is just the first one we'll ever see, but we always start our numbering with 0. And if you go to the library here and go to the section on, I don't know if they have it, but maybe they do, the Guinness Book of World Records, and look for the 2025 version, look, there's our survey, and there's their little JADES GSE13 right there. It says most distant confirmed galaxies in October 2022, astronomers, that's how they refer to me, astronomers. Call it JADES GSE13, and they say Z13 for short. We do not. My favorite aspect of this whole thing is that they've got this little box right here. I'm going to zoom in. This little box. Do you see where I've circled it? That's where it is in the sky. That's not where it is in the sky. And then they did an artist rendition to make it look really red. It should not be red. It's filled with baby stars. It should be really blue. It looks red because we're seeing it far away. Everything is wrong about this. It's okay, because when they printed this, they actually had not been up to date. This was the world record for a pretty short amount of time. We'll get to that in a second. Because I went and looked at all of the galaxies. And in fact, I've gone back for our full survey. Here is, just off the presses, from like a couple weeks ago, I submitted this paper. This is every galaxy in our survey that I have predicted to be above a redshift of 8. So we're seeing it in the first 600 million years after the Big Bang. This is a baby picture, showing you where all the baby galaxies are. If you want to know about the baby universe, here. This is like me saying, I went through a big crowd photo and took a picture of, painstakingly, found all the people who were born before 1970 or 1960 or 1940. Let's say that. I have to be very careful. And so this is the Hubble Deep Field, the Hubble Ultra Deep Field. This is over 2,000 candidates, which is very exciting. And they are weird. They're not like little smudges like the ones I showed you earlier. Here are real galaxies from my sample that I have finally given them silly names that I can tell you, but I can't put in print, but these are what I call them internally. I call this one I'm probably going to actually call the poodle in paper because I think it does really look like a poodle. The glowing dog bone. This one right here are two galaxies at about the same distance, and I'm showing you how far away they are in the sky. If this was, if I were showing you a picture of the Milky Way, the center of the Milky Way would be here and Earth would be over here. So it's showing you that our galaxy is huge, and these are two baby galaxies, both with clumps that are probably in the process of merging to form a much larger galaxy. This one, they have these big clumps. The universe is fascinating in early times. This is crazy to see so much structure when the universe has only been around for 500, 600 million years. Here's a galaxy that I found in the survey that when we passed this light through a prism, we saw this crazy spike right here. This crazy spike shouldn't exist. This crazy spike we shouldn't be able to see. Because when the universe was this old, or this young, it was essentially foggy. Foggy to light of ultraviolet, right? It has all that ultraviolet, like I just told you. All of those filters, that hydrogen that is pervading the universe should not allow us to see this. This is when I go back to that metaphor of putting on filters that you're like, now I can't hear the babies screaming in the hospital. Imagine if you could still hear one baby screaming really loudly. You're like, I shouldn't be able to. This filter's really, I paid a lot for these noise-canceling headphones. This object, this Lyman alpha emission right here, at a redshift of 13 should not exist. I showed this at a conference right after this was discovered, and multiple scientists came up to me and said, no, you're wrong. This can't exist. There's no way. And scientists have been scrambling to understand how the universe could essentially allow us to have one specific viewpoint of a galaxy where we are seeing this exciting hydrogen gas fluorescing. Really, really amazing. That every time we look at these data, we're finding things we can't explain. When I was looking at the data after I'd come up with my first sample, I found this object. And in February of 2023, I texted my then graduate student, Jake, saying, this is a true weirdo. I could not understand what this object was. It looked like it was at redshift 14.5. But it was enormously bright. And it had something weird, which is that it was behind, if it was that distance, it's behind another object. And it was significantly brighter than any other object at these distances. And I wrote about it in my paper. This paper I put out later that year, that was where I said it was a visually rejected candidate. I said, I want everyone to know this object exists. This is a weird object. I don't understand it. But there's no way it's actually the distance I'm predicting it to be at. Because if it is, that would be bizarre. So here's another picture of it. This red object, it has this weird other object kind of in the way, this red object. And the thing is that my grad student and I, we kept scratching our heads. What is this thing? Every time we'd go back and observe it with different filters, we were really confused by what it could possibly be. And eventually, they decided, let's just take a spectrum of it. Let's just pass it. It's bright enough that it won't be that big of a deal. We'll adjust our observations and just take a spectrum of it. Because if it turns out to be big, actually the distance, again, it won't be. It'll be a really big deal. But otherwise, it'll tell us how we can get things that trick us. What's going on? What is actually happening in this galaxy? Well, we get the spectrum, and it turns out it's actually at the redshift we thought it was, and it was, in fact, the record breaker. It was such a big deal that we got in the same paper, we also broke the record a second time, and that galaxy no one cared about because they were like, look at this big booming one. This object, you can see the cliff right here, this object is at redshift 14.2, and it broke our own record. It came out, and we had it, I published it before they could stop the presses on the Guinness Book of World Records. And it came out with another one. And so for a little while, this was a really nice marketing material for the University of Arizona because Kevin Hainline discovered number 1, number 2, and number 3 farthest galaxy humans have ever seen. Pretty big deal. And so let's fly there. Let's fly to the farthest galaxy. Let's fly to JADES GSC 14. This is a video I helped put together with the Space Telescope Science Institute. Every one of these objects is a real galaxy from the survey at the predicted distances that I gave them. And as we fly through them, we will see that we are flying past a lot of little faint galaxies that are pretty close by and bigger galaxies are close by as we go farther back in time to when galaxies were simpler. Their shapes were complicated but not nearly as big. They were much, much smaller little nugget galaxies that were still forming in a baby universe as we travel all the way back to what was, at the time of its discovery, the farthest galaxy humans had ever found, JADES GSC 14. And one aspect about this that helped us really get to go was that my grad student Jake came into my office and said, hey, Kevin, you know this object is booming and mirroring? You know, we have a picture of this with MIRI in our data, and it's actually brighter in MIRI than it is in NIRCam. And he showed me this right here. And he said, this is what it looks like in NIRCam. This is its little neighbor object. This is how bright it is in MIRI. And remember, at the beginning, MIRI was the instrument they were going to take off the telescope. MIRI was the instrument that wasn't going to be valuable. MIRI was the instrument that no one ever thought it would ever see anything this far away. I didn't even. I thought it would cap out at 8, and here it was showing an object that could be at redshift 14. And we did the math. If this were at redshift 14, this booming light here would come from oxygen gas. Oxygen gas in a galaxy when the universe was only 290 million years old. So Jake wrote a paper about this. We got time on the telescope, and this is also hot off the presses just from last month. This right here is the spectrum from MIRI showing starlight, which is what you're seeing here, starlight, and the oxygen gas booming, and a little bit of hydrogen gas over here as well. Booming oxygen gas when the universe is only 290 million years old. And why that matters is that oxygen gas comes from stars exploding. Meaning, in the lifetime of the universe, stars have to live their entire lives and explode, give up, create oxygen gas, enough of it that it can go into this baby galaxy and a baby universe. It's as if I said, look, I have this ancient Roman site, and we found an iPhone in the ancient Roman site. How did they get an iPhone? Well, a lot of stuff has to happen. Oxygen doesn't just come on the scene. You just breathe it. You're like, it's just like oxygen. No, oxygen needs stars living and exploding. And it helps us understand the exciting nature of the early universe. Now, I will say, JWST 14, the record was taken by another team, the Miracle or Mirage team, MOM, with this galaxy, MOM Z14, that actually broke the record. And just last week, a bunch of press releases came out about it. So it's been in the news a little bit, but it does, in fact, break the record. You can see the drop-off right here. I will say, all of these little dashed lines show it has a lot of ionized gas in it, and the work that was done to identify that was my former grad student, Raphael, so I did have a little bit of part to play in this. I'm joking. This is an incredible research discovery, and it takes the heat off of me. There's nothing like being nervous, like having a world record. Here is a plot showing all of my candidates. Not all of them. I have more, down here. I just wanted to show the highest redshift candidates. All the big circles are objects that have been confirmed. But every little circle is one of my predicted ones. And the y-axis here is how bright they are. So the intrinsically brightest one, and this is intrinsic brightness, meaning not how bright they look to us, but how bright they actually are. So you're seeing that as you go to higher and higher redshift, there's not as many super bright galaxies. They kind of fade out. But you're also seeing that we're actually not able to see the faintest galaxies farther away, which makes sense. And most of the ones that we've confirmed are the brightest ones. But there's a whole population of pretty faint objects that we'd still like to confirm. And exciting for me, a bunch of objects that I have over here that would be record breakers, that would help us understand even farther back in time, right? So this is JWST 14 I just showed you, and then the one that's the current record breaker. And I want to show you something. This is also hot off the presses, and I'm showing you this, and it might be a little bit egotistical to show this, but I'm very proud of this. But this object right here, which has got a horrible name, and I just generally call it 1019411, this object right here could be at a redshift of 16 and a half. 16 and a half would put it, way over here. And I have, you see it here, it's really faint. You see it, you don't see it in any of these filters up here. It looks like it could be, it has a lot of evidence that it could be. And then when I was writing this paper and looking at this object, I realized that our team had already taken a spectrum. We'd passed this light through a prism. I pull that up, and it's really tough to see here. Really, really not a great spectrum. I don't see that same cliff, right? Like when I look at this, you really see the cliff right there. And I have some things to guide the eye to where it should be, but I published this. And the day that I published this, one of my colleagues said, you know that another team has sneakily gone and observed, this is like a 2-hour spectrum. They've done a 28-hour spectrum of this object. And I'm telling you this because at some point in the next month or so, a team might come out and say, we broke the record, 16 and a half, And I'm telling you, you all knew about it first. I found it. Here it is. They're just confirming what I'm already showing you. So I know I'm out of time, but I just want to talk about why we care about this. This is a plot showing the Big Bang and time going on, but I'm only showing the first 1.5 billion years after the Big Bang. Look at all the stuff that happens, all this stuff that happens. you get a period where the universe is just hydrogen, and then it's cooling off, and it's opaque, and the first stars and galaxies are appearing. You're getting the first black holes. You're getting the formation of structure and spiral galaxies, all in the first 1.5 billion years. It's a very exciting time. And we only know about this in the last 20 years, and really only know about much of this in the last 5. And it's through JWST and many, many teams. I'm very biased in showing you the JADES view, but there's lots of other teams that are finding this independently in their own sight lines. The Miracle Mirage program is looking at a different region of the sky where they found their farther galaxy. It's very exciting that we're all uncovering this because this is when structure and formation happened that led to you being here. You've no doubt seen the periodic table of the elements. I'm coloring this periodic table by how the elements were formed. And I want you to look at things like carbon, nitrogen, oxygen, things that you are familiar with here on Earth, right? Hydrogen and helium, Big Bang, easy. That's what's made in a Big Bang. Everything else requires stars to live and stars to die. Carbon right here requires dying low-mass stars, like I showed you at the very beginning. That's how you were made. You were put together inside, atom by atom, inside stars that lived their lives and died. And we can see this with this telescope. Oxygen that you're breathing, exploding massive stars. This is how we were made. And that story is only something we've known in the last couple decades, really and truly. And so this is what you as American taxpayers help to pay for, is our ability to know where we came from. If you've wondered, why are we here? How did we get built? We know. We can see it. We can take pictures of it and watch as the universe builds in complexity, not just visual complexity, but chemical complexity. It's really fascinating. And because you paid for it, the data is yours. JADES is entirely public now. You can go to this website, jades-survey.github.io, or just Google JADES survey and find the website. And you can click on our viewer and just go look at all the galaxies. Zoom in. This is something where I just had it on my browser and took a screenshot. You can zoom in on every single one of these dots, click one of these little hamburger icons, and it'll show you properties of it. You can find spectra, SEDs. If you are young in this audience, you can take all these and go crazy with a machine learning technique to try and identify and characterize and, don't all of you do this, but you could hypothetically find interesting ones and then email me and say, Dr. Hainline, what's this? And I will tell you it's most likely a brown dwarf. That's the weirdest things in here. When you find brown dwarfs, they're super weird. I have a second entire hour-long talk I could give that I won't about the brown dwarfs in this, but it's a very, very exciting data set, and we've really just touched the tip of the iceberg. A lot of the stuff I was showing you looked pretty amazing, but it was the lowest hanging fruit. There's people here, maybe, maybe young people who don't realize it, but they will get their PhD in part looking at these data. That's the exciting part about this, is that I'm just showing the tiniest little part of what is an enormous, 1,000-hour data set. So I'm going to finish here and answer questions, and I'll stick around for a little bit afterwards, but then I urge you, please do come to learn more about the making of this telescope and the people who helped design it and help launch it and stuff. I'll show some fun pictures, tell some behind-the-scenes stories, and I'll be sticking around. But thank you very much for listening to me talk about this exciting day. So I see some hands going up. I can answer a couple questions like this, but I'll also stay down here so that, to answer questions if you have ones where you're a little bit embarrassed to ask them in front of everyone else. So I saw this hand right here. Yes. So dark matter doesn't interact with light at all. We don't know what it is, and light just passes right by it. Dust interacts with light all the time. Dust is essentially carbon and oxygen atoms combined. We call them, and hydrogen, called them hydrocarbons. And it's like soot, like the type of soot left behind after you run a barbecue or something. If you were run your finger there, that little soot floats through space and it's dust. Dark matter does not interact with light in any capacity except gravitationally. And so we don't know what it is right now, but we know that it affects things gravitationally. There is a lot more dark matter than there is dust in the universe. There's a lot of dust, but there is, many, many times the amount of dark matter than there is the matter that we interact with on the Earth, right? Dark matter composes about 1/4 of the mass of the whole universe, and we do not know what it is. And if you have more questions about it, I'm the wrong scientist to ask. You're going to have to ask the library to invite a dark matter scientist to come out and talk to you about that. Yes?
Yep. Is there a constant speed at which gravity
The galaxies are flying away from the Earth, and it always seems like we're the epicenter because we don't feel that we're also moving. Everything is all moving, right? And it's also all relative. So it all looks like they're all moving away from us, but there's not an epicenter because the universe is infinite in all directions. So there's not like a center. But we do know that the farther something is, the faster it's moving, and this is called Hubble's law. And it's just a simple thing. The velocity is equal to a constant we call Hubble's constant times the distance away. And this is another thing that you should invite someone else who's not me out. But that number of the Hubble's constant, there are two camps based on two different ways of trying to answer that question of what that could be. One camp says it's about 72 to 74, and one camp says 68, 60, and they are it's called the Hubble tension, and we don't exactly know, but God forbid there's ever a Hainline tension. I mean, there is sometimes when my wife and I have arguments. But I'm saying that that allows us to do what we do, which is that the galaxies that are farther away are moving faster just based on this h0 d. And the reason the Hubble h0 is the Hubble constant and the distance. That's why I don't tell you the distances to the objects. I just tell you the redshift, because the redshift doesn't depend on the Hubble constant. We don't care about the Hubble constant, except that I'm telling you the velocity, some fancy way of telling the velocity. Other questions? Way in the back. Yes. Yep. Okay. Webb will hopefully live, JWST will hopefully live, it was designed to live for 5 years. Now, it's almost been that time. Luckily, it was launched so well that it'll probably live for about 20 years. It's defined by the amount of fuel. And so, imagine if you just had one tank of gas, and it was you need to go to a spot and park. And then once you're there, you turn your car on and idle it. And however much gas you have for idling, that determines how long you can listen to the radio. With JWST, it was launched so well, they parked it so well in L2, it has lifetime for 20 years. Now, something awful could happen, micrometeorites or some failure of a mechanism, but for right now, we're hoping for a really long lifetime, which is great. We're about to hit the 5-year mark, which would be a real win for the fact that we've done our nominal lifetime. Hubble's a different story. Hubble orbits our planet. We could go out and fix it. The problem, and I don't want to get political here because I don't know, but I don't know if you're aware, but the government doesn't care as much about science in the last couple of years as it has before the last couple of years. And the NASA budget has been on the chopping block. And in order for us to go and fix things like Hubble, we have to have money to do that. And so this is a reason why we pay taxes or why we support things with our voting and with our, calling to representatives, why we support things like this, because we only are able to do this because, this is very, very expensive to do. This telescope cost $10 billion. It was I should say $10 billion for some people is not as different than $10 billion for us NASA folks, but $10 billion is a lot of money, and this was a very, very huge effort through multiple countries. So Hubble is something where we could go and refuel it, put new instruments on there, and keep it up there. It depends if the right people don't intercede and work on it, it will at some point spiral in. It's gone well past its original stated lifetime, but we've gone up there many times to fix it. Now, the last times we've gone up to fix it, we had space shuttles. We do not have a space shuttle program right now, so that is a problem. Is how might we do that? But we cannot go to do that with JWST. JWST was not designed for us to grab onto it and fuel it. It doesn't have a really accessible little fuel pump spot because we didn't think we would have to do that. Other questions? Yes, right here. So here's the thing about Hubble, is that the American government said to the astronomy community, hey, we have this former spy satellite that we never, sorry, that's the wrong term. Not former spy. We don't spy on ourselves. We have a telescope. I don't know what it's for, why we have it. Do you want this shell of a telescope that's about Hubble size? And then the astronomy community said yes and modified it. And in the next decade, we will have the Nancy Grace Roman telescope that will launch that will be essentially kind of like a JWST, a much smaller mirror, Hubble-sized mirror, but it will allow for a much bigger field of view. So where Hubble was limited in its wavelength range, the Roman telescope will be able to see into the wavelength range that partly into what JWST can see. It won't have the resolution, it won't have the light gathering power, but it will have an enormous field of view, which means it can take really wide area pictures, which is great for getting a lot of data also. So the answer to your question is we'd love to have more of these telescopes, but getting another JWST is very, very difficult because of how complicated. Again, documentary in an hour to really show you, or 2 hours. But JWST is something that there are people in the works who are thinking about what our next big project like that is. But for right now, we're relying on some projects that are in there, about to launch pretty soon, like the Roman telescope. Yes.
From the point of view of intelligent life,
Mm-hmm.
when you talk about what it takes to form us and form
Yep.
That must happen everywhere, not just in the
I would think so, but then the question is, why aren't we cool enough for them to talk to us? What is it about humans and Earth that makes us like no one is sending us signals? And that's the big question, the Fermi paradox, right? If you have all these aliens, why aren't they talking to us? And now I hear people saying, well, they're far away, and I get it. Aliens are far away, but light travels, and in the next 5 to 10 years, we're going to have a pretty nice sample of planets that have pretty good evidence of having some form of life going on them. And the thing is why aren't we constantly being hearing them? And I don't know. The answer is, what I really worry, I don't want to finish on this, so I'm going to answer a bunch more questions after this, but I really worry that life, the life that we have here on our planet, all we have to do is just be really loving with each other and our neighbors and the natural world, and we could live for a long time. But thank you for the smattering of applause. But humans want to make it a little more complicated. And so what I worry is that life inherently is something that sees, even if they could work in concert with nature and with the natural world, and sees that there's enough to go around, thinks of it as, no, we have to have this competition. And so what if life is like a little blip, like a firefly, and we just didn't get lucky that there wasn't another life that was around in the time? The universe is 14 billion years old, 13.5 billion years old. There's been a long time. Maybe we're just not lucky to see that one little blip. But I also just maybe think that aliens, I'm hoping maybe alien life is not like us, and that maybe they're more like trees. Trees don't care about space. They love talking to each other through their roots, and they love the wind, and they don't need to look at space. We think that that's what, no. There's a lot of complicated things when it comes to aliens, and I'm not an alien specialist by any means, but I'm glad I said specialist there. I'm not an alien specialist by any means right there, but I would love for us to find them. Maybe they're waiting for us to figure our stuff out and stop being so excited about digital watches or whatever, and start, then we can really, then they'll talk to us, or maybe we come with, maybe it's a zoo. Maybe aliens look at us in the same way that you did not step down and say hi to every ant you walked by when you came into this, library. They're like, what, humans have a long way to go. I don't know. But you're right. The answer is this thing I showed you, it's happening everywhere. We are finding that almost every star has planets around it. And we're finding that it's hard for us to find planets that are like the Earth, only just because it's hard for us to find them because they're so close to their stars. And yes, all right. You have a question? Oh, you're an alien? I will. I'm doing a dramatic question answer. So give me a second. And the thing is that the Earth is incredibly precious, and I'm hoping there's many, many other Earths like it, because we have to hope that there are aliens out there and that we're not alone, because it puts a lot of pressure on us. Okay, so now I'll answer your question. Yes.
Thank you. This is sort of related to what he just was asking as well. So based on what you've told us thus far, we've got the time travel of light, wavelengths.
Sure.
We have all been evolved in some way, shape, or form from the destruction of these stars.
Yeah.
So is it possible that we are seeing things in different dimensions? So when we see the stars thousands or millions of years ago that have been destroyed, and then the light gets to us, could it possibly be in a different dimension? So back to the aliens and people that are living on these other planets.
Dimensions has a thing that people use in the media and in movies that's very different than the way that dimensions should be. Dimensions to us and to scientists is the fact that there's up, down, left, right, forward, and backwards. 3 dimensions of space, and then a dimension of time, right? And the light we're seeing, one of the cool things about all of I'm showing is that we're not just looking at it and seeing it and being like, wow, that's the only place it's like that. Everywhere we look, it's like this. The fields that I'm showing you, JADES, that field, and I can, that field of JADES is like 2 grains of sand at the end of my hand. And anytime if we were to point anywhere in the universe, we'd see the same types of diversity of galaxies and distant galaxies and stuff like this. And what that leads me to believe is that we're not just privileged to look in one direction. So if it were looking in other dimensions or something, we'd have to be looking, or other, it would be very weird that it'd be all over the place. But we're not the only people doing it. Other scientists are looking in different regions and seeing very similar results, and it's all coming to show us that it's in agreement with our understanding of the universe. One of the brilliant parts about this is that our theories for how the universe is changing and evolving, how galaxies are being formed and evolving, those theories are pretty much in line with what we're observing. They have to be tweaked because we find new observations and stuff, but we don't have to invoke alien dimensions to help explain things. Generally, we evoke like, oh, actually, this is a little more complicated, and it's because probably this is slightly changed, right? Like, we do a pretty good job without needing to, ever evoke aliens trying to trick us with multidimensional, cameras to us. Now, maybe they are, but again, wrong person to ask to come out and talk about that. I'm pretty happy with how good we're doing at finding all this without needing to say, actually, this thing we're seeing here is in another dimension. Like, no, it's in ours, and it's just, thousands of light years away, and it's a pocket of gas that's slowly cooling and coalescing, which is pretty exciting in and of itself.
But it relates to this second part of my question, which is it possible that what we're seeing ourselves today is still going on way out there and the light just hasn't reached us yet? So the evolution of mankind here on Earth.
I would need to, let's talk afterwards because I don't understand your question. Sorry. I also, people, if you need to leave, you definitely can. And I appreciate everyone who's, I won't be offended. I know that this is a lot of questions. Yes. Oh. So the Big Bang was 13.5 billion years ago. The universe was born in a giant explosion of light energy. And if you're wondering what happened before the Big Bang, you need to bring a priest in, or or a philosophy professor, because all we know is what happened up to seconds after the Big Bang. But it was an enormous energy. The entire universe was all light at that point. It was sent off into its initial explosion, and the galaxies were sent expanding away from each other. But the galaxies didn't exist at that point. It was just all light. The light cooled as the universe expanded, and it cooled, and from that light was formed particles, and from those particles was eventually formed the gas that went into the first stars and galaxies. And so if I back up to show you this, this right here is just we don't know why it happened. We don't know. It happened everywhere because the Big Bang was omnipresent in the universe. And again, this is the realm of philosophy and religion. And I am a person who's been looking farther and farther back to find some of these first galaxies and structures. There's going to be a period where we're not able to see galaxies before then because the universe, first off, didn't have galaxies, and it was entirely foggy to just light itself. And we've already seen that last scattering thing right there. But we're seeing all this structure. What happened here? Do not know. We know physics-wise how how all of the various forces came to be from this, and that's again another entire talk from a theoretical physicist that I will tell you will be kind of boring. It's very complicated, very, very difficult, but we know all this. But once you go to a fraction of a second after the Big Bang, before then math doesn't make any sense. Our science doesn't make any sense. Oh my gosh, yes, right here. Yeah, so you're lucky to want to do space science because we're going to have a lot of space to do science with, which is very exciting. And my main thing to say is when I was younger, I wanted to do space science really, really badly. And the thing is there's lots of talk about which college, Mostly what's important is that when you go on and get an education after, when you're taking classes in junior high school and high school and stuff, you try and take classes that aren't just the easy ones. Challenge yourself, not just with science. To be a space scientist, to be an astronomer, you write more than anything. Writing was so crucial. Not just writing, but my English classes. Reading, comprehension, understanding how to read and understand things. I went to a high school in Orange County called El Medina. My dad went to the same high school, just a public high school. And I remember so much of my English classes. I remember the first time someone put The Sound and the Fury, Faulkner's The Sound and the Fury in my hands. And I was like, wow, people can write like this? Really important. More than I remember my calculus classes or my chemistry classes or biology classes. But I took all those classes. And then when you go to college, I did the same thing, which is first off, I applied for a bunch of colleges, was rejected from all the colleges, worked at the Main Place Mall for a year, then reapplied to college, went to San Andy Community College, went to Harvey Mudd after getting in after a year. And I did the same thing, which is take as many classes. I have to do this over here. I'm not being rude. It's just very hard to talk to you while I have this microphone because you're right here. I tried to take classes that were outside of what I was just doing. And I tried to also, when you were in college is when you get your first chance. And in high school you can as well, with astronomy research. You live in a time where it's never been easier to take raw data and explore how to use it and look up, you should be learning, and if you want to do astronomy, and I know this is a really rote thing, you should be learning how to code in Python. You should be learning how to open up a Python, like a document, open up a Jupyter notebook and code in Python, read in an astronomy image, and plot it. And it has never been easier to Google AstroPy, astronomy Python tutorial. Heck, and I probably shouldn't say this too loudly. If you were to go to ChatGPT and say, hey, ChatGPT, can you teach me how to code and open up Python? I guarantee you it will teach you the basics on how to do this in a way where you say, hey, can you do it in an iambic pentameter? And it would do it in an iambic pentameter. And burn down a rainforest to do it. But you can do that. And that allows you to, you can go and take JADES data and open up. You could, within, I could sit down with you, or you could do it on your own. Within, an hour, open up my catalog and plot and find all the highest redshift objects in our catalog. Just because our data is public, and it's a FITS file, which is the format we use, and just having familiarity with that, really helpful. Because when I sit on committees for students applying to go to grad school and stuff, all I want to see is that they never wasted the beautiful opportunity you are given of being young and having classes and being excited about possibilities. I never want to see a student who's like, well, college was awesome. I learned how to play beer pong. Nope. I want to see someone who's like, I was on this club and I was part of this. I ran this. I wrote poetry. I made art. And I also wrote papers and did this. I want to see that they do a lot of stuff. And astronomy will always be there. You will always probably have to use coding to explore it because there's so much data. We live in an era where machine learning is a very exciting thing as well. There's a lot of galaxies, getting into that. But really, it's just being passionate and never letting a person say there's no money in it. Because I'm going to tell you right now, there's no money in it. But you don't do it for money. You don't do it for money. You definitely don't do it for money. You do it because it's inside of you and it has to get out in some way. You have to do it. And that, if you ever find yourself looking at a thing you want to do, young person, and you say, I don't like doing this, don't do it. That's what's cool about being alive, is you should only do it, especially astronomy, if it's I can't imagine doing anything else with my life. The instant that you're like, actually, what's really awesome is singer-songwriter, then go do that. There's even less money in that, but my wife's a singer-songwriter, and it's... Together, we are amazing couple of, science and stuff. But man, no money for it. But that's okay. We love to do it, and because we can't imagine our lives any other way, right? So my answer to you is that, just be passionate and learn a little bit of Python coding and play around with data. Play around with public data. There's so much public data and only going to be more public data. And read online, read websites, read Astrobytes, which is grad students writing about articles. They write about scientific articles and make them more easy to understand. Read, news articles about these. Just Google the things you care about. Go and follow, JWST on Instagram and look at all the beautiful pictures from there. And don't just look at them as a picture. Go and find out, what does that actually mean? What do the colors mean? All this is accessible. We've made it, it's never been easier to be a dork about astronomy than it is right now. As a dork about astronomy, I can say. Yeah, thank you. In order for everyone to get out, I will answer questions up in the front, but thank you all very much.
Thank you so much, Dr. Kevin Hainline. Again, he's going to answer some more questions up front. We are setting up for giving tours in the observatory. We are all set for you guys out there. Feel free to queue up out there. Likewise, again, that last question, ditto to everything he said. He's spot on.